Let me introduce you Dr. Radin from Duke University. She worked with Dr. Austin from the MIT. They are presenting their entry optimized scoring systems toward trust in machine learning for healthcare and criminal justice. Thank you.
Thanks very much. So when this article came out last summer, I couldn't get over it. Actually, at the time, Burke and I were working on interpretable models for recidivism prediction, and this article by ProPublica accused the Compass recidivism tool of being racially biased. Now, Compass is a predictive model used widely throughout the US justice system for predicting recidivism, and it's completely proprietary. It's a black box. Nobody can see inside of it. It's owned by a company called Northpoint, and whenever Compass is used to make a prediction, Northpoint makes a profit. And ProPublica gave this example of this young woman who has a small criminal history labeled as high risk, and then that guy who likes to commit armed robberies is labeled low risk. All right, so there was a big debate in the media about this, and this group from Stanford sort of kind of sorted it out, and they basically said, well, Compass might be biased, but we can't tell. And they said Northpoint has refused to disclose the details of its proprietary algorithm, making it impossible to fully assess the extent to which it may be unfair, however inadvertently. And that's understandable because Northpoint needs to protect its bottom line. But I don't care about Northpoint's bottom line. I care about the quality of our US justice system. So it kind of makes you wonder, like, should we be using black box models for these kind of high stakes decisions? When the government is outsourcing these high stakes decisions to companies without any structure around it, it causes misaligned incentives. And ProPublica brought up the issue of fairness. There's another issue that was brought up in a New York Times article over the summer where this was a case of a model prisoner, Glenn Rodriguez, who was denied parole, and he doesn't know why. And he goes back and he figures out that, in fact, his Compass score was calculated incorrectly. And this happens fairly often. So what's going on is that typos are making our high stakes decisions. All right, there's a question of whether Compass violates due process. And this court case went all the way to the US Supreme Court that denied to hear it last month. But essentially the idea is that, you could be in prison and you don't know why, and you have no mechanism to argue with it because it's proprietary. So those are the kinds of reasons why laws like the right to explanation law in Europe has been enacted, where algorithmic decisions about individuals need to be able to be explained. And there's a similar law in New York City that was just announced. Okay, so if we had transparent models or glass box models, then, these issues would sort of go away, right? So it makes you wonder, well, are there transparent models that are as accurate as the black box models, right? Northpoint is not incentivized to produce such models, but maybe such models do exist. And if they do, how would one create them? Okay, and it's not like there's no transparent models out there, right? There's a long history of transparent models in medicine and in criminal justice and in other fields like credit scoring. What I'm showing you here is the Chads2 score, which is possibly the most widely used predictive model in medicine. It predicts stroke in patients with atrial fibrillation. You add up the points, and then the score translates into your 1-year risk of stroke. This is the heart score. You add up the points. It translates into your risk of having a serious coronary issue. This is the violence risk appraisal guide. So this guy, when you add up all the points, it translates into low, medium, or high risk of violence. And I've just listed a few of them here, but there are hundreds of these scoring systems in medicine, in criminal justice, and credit scoring, and many other domains. Now, all of these models are of the same form. They're all scoring systems. Each of these models was created in a different way. None of these models was optimized for predictive performance on data. Some of the models were created using domain expertise alone, without data. And some of them were created using complex pipelines that involve sort of rounding logistic regression coefficients, and then you look at the model and say, oh, I don't like it because it's not interpretable or it doesn't obey constraints, and so we change the coefficients and then we re-optimize and re-round. It's not what we want to do. Rounding, of course, by itself leads to problems. Anyone who's taken a class in discrete optimization knows that rounding leads to violation of constraints. It leads to low-quality models, particularly for regression. If you round the coefficients, if you have many small coefficients, they all get rounded to 0, and you lose an entire part of the whole signal. So we said, OK, maybe we could try to learn scoring systems directly from data, avoiding all of these heuristics that people use in these complex pipelines that take forever, and we can just do it in a principled way that can be used across different domains. So what I'm going to present today are two machine learning methods. They're called SLIM and RISC-SLIM. They produce scoring systems directly from data. OK, so SLIM is for decision making, like yes or no decisions. It uses mixed integer programming, whereas RISC-SLIM is for risk scores, and it uses a cutting plane algorithm to solve a min-LP. And so I'll go over that. Let me just show you this example of a SLIM model. This was built from the largest publicly available data set on recidivism. It predicts whether somebody will be arrested within 3 years of their release. This model, you add up the points, and then if the score is above 1, you predict that the person is going to be arrested within 3 years. Okay, so it's a decision-making model. Let's show you also a RISC-SLIM model, where you add up the points, and then the score translates into your risk of recidivism. Now, both SLIM and RISC-SLIM can accommodate any number of constraints that you might want to include. For instance, if you want the false positive rate to be not more than 20%, you can just include a constraint that will force that to happen. You also might want monotonicity constraints, for instance, where if you want the score to increase as, say, the variable age increases, and you can just put that in as a constraint. Okay, so let's talk about SLIM for a little while. Now, SLIM's predictions are yes or no predictions, like will you be arrested or not. You'll be arrested if your total score is above a threshold. And the coefficients are 2, 2, 1, minus 1, minus 1. Those are the lambdas. And those are going to be learned from data. The data look like this, where you have ground truth for each observation. SLIM solves a MIP, and this is the optimization problem that SLIM solves. It says minimize a combination of error and sparsity. So this is the error rate. This is the fraction of times the prediction does not agree with the truth. And then this is a sparsity penalty. It's just the number of non-zero coefficients in the model. So keep the model accurate, keep it sparse. We'd like the points to be within a set of integers, small integers, here between -10 and 10. And we would like the greatest common divisor of the coefficients to be 1, because rather than having scores of 3, 3, 6, and 9, we would prefer to have scores like 1, 1, 2, and 3. Okay? But putting this GCD constraint into a MIP is a little bit tricky. So we had to find another solution. And luckily, there's a little trick, which is that if you add a very small L1 penalty, just the sum of the absolute values of the coefficients, if you add that to the objective, that will get you coprime coefficients without any other sacrifices, as long as epsilon is small enough. So among equally accurate and equally sparse models, this will find the coefficients that are coprime. All right, and then the solution to this is a super sparse linear integer model. All right, so here's the MIP, just so that you can see it exists. And it happens to be tighter than other MIP formulations for classification because the big M constraints are actually much tighter because we're using small integer coefficients. We also have a set of bounds that allow us to discard large amounts of data and preserve the solution. And we also have probabilistic guarantees on out-of-sample performance that come from statistical learning theory. And in particular, we can use number theoretic concepts like Fairy numbers to help us prove better out-of-sample guarantees because the coefficients are small integers and coprime. Okay, so let's talk about risk slim for a bit. Now, risk scoring models have been around for about 100 years. This is the Burgess model for predicting success or failure on parole from 1928. And I love the way he groups people into categories like farm boy and recent immigrant and drunkard and mean citizen. And so, but anyway, it's a risk scoring model. So you add up the points and it translates into your risk of violating parole. Okay, so how do we create a risk scoring model in a principled way? Well, we're going to minimize this is the logistic loss that's used in logistic regression, and that helps the scores be calibrated. And then we have a term that also, again, handles sparsity, again, small integer coefficients. This is a MinLP. If you give it to a MinLP solver, it will take until the end of the universe for even a reasonably sized problem. Not a good idea. So we tried to do something else, which was to use cutting planes, but we ran into a problem and had to make a change to the algorithm. So let me talk about that. So cutting planes have been very successful in support vector machines and other types of machine learning problems where you're trying to minimize a convex function. Okay, so how do cutting planes traditionally work? Well, let's say we're trying to minimize this nice convex orange thing. What we would do is create this piecewise linear surrogate function, send it to an LP solver, and get the minimum. And then we would evaluate the function at that point, create another cutting plane, add it to the set of cutting planes, resolve the LP, and then continue to do this over and over again until the minimum of the surrogate matches the minimum of the objective. Matches the objective value. Then you know you've gotten the minimum of the objective. But for us, the solution of the LP is not what we want. In fact, we want that point over here. Okay, why do we want that point? It's because our feasible set is the integer lattice. Okay, so we have integer points. So now we have to solve a MIP at every iteration of this cutting plane method. And we have to solve it to optimality, because if we don't solve it to optimality, we will never know when we've reached the minimum of the objective we actually care about. The problem is that once you have enough cutting planes, it's very, very hard to solve this MIP. And you get this stalling behavior. So here's an example where we ran the cutting plane method for 70 iterations, and it took 10,000 seconds, and then we stopped it and said, forget it, this is not going to work. And then, because you see, the problem only gets harder and harder as it goes on, because you just add more and more cutting planes. So if it doesn't solve here, forget it, it's not going to work. So we came up with a solution to this problem, which is a new algorithm that combines cutting planes with branch and bound. Okay, so here we're going to solve the LP. And then we know there are no feasible integer points in here, so we can actually subdivide the feasible region into these different subsets. Now, if the LP happens to land on a feasible integer point, we could create a cutting plane. But if not, we continue to subdivide. And this solves the problem. So here, after 70 seconds, the solver choked. And now we can go, even if you go up to 10,000 cutting planes, the solver solves it in under 100 seconds. And you can see the optimality gap is now finally going down towards 0. Okay, another major benefit of using cutting planes is the fact that they scale really well with the sample size. So, even if you use, say, 10 million observations, the time spent on the solver doesn't change. Okay, so why is that? It's because the solver never sees the data, right? The solver only sees the surrogate function. The data gets used to calculate the surrogate. So the method does, it does require the data, because you have to calculate the surrogate at every iteration. But now it only scales, linearly in the amount of data. So even if you have a problem that's 10 million observations, you can still solve it on a laptop in 15 minutes. All right. So let's talk about some applications that inspired the work on these methods. And the first is recidivism prediction. Now, we could use just plain judges to do recidivism prediction. But the problem with that is that judges are very biased. They're racially biased, they're inconsistent within a judge and between judges, and they cannot keep an entire database of anything in their heads and calculate risk scores accurately. Okay, COMPASS, we know the problems with that. Let's try SLIM. Okay, so again, we're using the largest publicly available data set on recidivism. And we were trying to solve 5 different prediction problems. We want to know whether someone will be arrested within 3 years, whether they'll be arrested for a drug crime, a general violent crime, sexual violence, or fatal violence. We restricted the SLIM models to have at most 8 terms, and again, of course, integer coefficients. And then we also applied the usual arsenal of machine learning weapons to the same problem. Okay, so here are the results for the problem of predicting arrest. And what you'll notice is all the machine learning tools are performing almost exactly the same. This is an ROC curve, so you want to be up in that corner. But all these curves are all on top of each other, okay? So all the methods are performing the same, except for maybe CART. Right? Some of the green methods, the older methods, don't maybe perform as well, but you would expect that. Okay, here are the results for general violence. Again, all the methods performing the same, except for the kind of the older decision tree methods. All right, so that handles accuracy. What about interpretability? Okay, what about transparency? Now, what we did was we chose a spot where all the methods were performing pretty much the same true positive rate, same false positive rate. Let's look at interpretability. Well, some of these methods, you just can't write the model on a slide, like support vector machines with radial basis function. Forget it. But you can put the CART model and the lasso model up on the slide. And here they are. Now, I don't feel comfortable explaining these models to an audience, let alone a judge. But I would feel much more comfortable explaining the SLIM model to the judge that I showed you earlier. All right, so the bottom line for recidivism prediction is that standard machine learning methods, they can't incorporate constraints, for example, interpretability constraints. They're much more difficult to use, and if you care about constraints, and they don't guarantee optimality of any form. This is just the header of our paper in the Journal of the Royal Statistical Society. And at the moment, we're working with the Laura and John Arnold Foundation, who are producing a very large data set for us to sort of design recidivism prediction tools on. These guys have a history of their recidivism tools being widely used in the US. And then this work is presented at the National Academy of Sciences in the Sackler Forum on Machine Learning. And it gives very strong evidence as to why we do not need anything like COMPASS in the US justice system. Okay, so let's switch applications over to sleep apnea. And this is work with the doctors who run the sleep lab at MGH, Massachusetts General Hospital. And they explained to us that obstructive sleep apnea is actually quite serious. It causes a whole bunch of other medical conditions, and it often goes undiagnosed. So they challenged us to try to create an accurate, transparent model for OSA that obeyed certain operational constraints. Like they wanted the maximum false positive rate to be about 20% because they were going to use the model as a screening tool. And if the patient passes the screen, then they would be given a polysomnography test, which is a definitive test for sleep apnea where the patient has to stay overnight and get monitored, and it's very expensive. And you don't want to give that to too many people who don't actually have sleep apnea. So they didn't want a false positive rate more than 20%. Size at most 5. We had certain monotonicity constraints, like they wanted, if the amount of snoring was in the model, then they wanted the score to increase with the amount of snoring. Okay, so the second question they asked us was, what is the value of the patient-reported symptoms like snoring or gasping or insomnia as compared with information that they could easily get within the patient's medical record? Right? You'd think that things like snoring or gasping would be really good indicators of sleep apnea, but it turns out they're not. Actually, things like hypertension, that's much more predictive of sleep apnea. Okay, and they gave us a fantastic data set. We had all patients above 18 years old who took a polysomnography test at the sleep lab within a 4-year span. And we had their whole medical records, and our goal was to predict the outcome of the polysomnography test. Okay, so again, we tried the usual, set of machine learning weapons, and they all perform the same. This is SLIM in blue, and support vector machines with radial basis function kernels in red, and across the full ROC curve, you get identical predictions. Like this is one of the most black box models. Okay, SLIM, on the other hand, produces models like this. Okay, so this model, you might think, okay, all the points are even, they're not coprime, but actually this 1 is lambda 0. So between the 1, the 6, and so on, they're coprime. The false positive rate is bang on 20%, which is where they wanted it, thanks to the constraint we put in to the objective, so the optimization problem. And then it was solved to optimality. Now the doctors looked at this scoring system, and they created their own rule-based version of it so that whichever one they felt was more easier to use could be used. And one thing you might notice is that there are no patient-reported symptoms in this model at all. There's no snoring, no gasping, nothing like that. And we noticed that the other machine learning methods were actually using the patient-reported symptoms. So we were wondering, well, what is the value of these patient-reported symptoms? So we did a little study where we used all of the features and produced ROC curves and got this gray curve. And then we removed all of the patient-reported symptoms and got this black dashed curve. And as you can see, they're right on top of each other, which means that we did not actually need the patient-reported symptoms. We also did another experiment where we took out the medical record and just left the patient-reported symptoms and got this black curve, which is not nearly as good. Okay, so the doctors were really excited about this because what it means is that it opens the door to automated screening for sleep apnea. If you have the patient's medical record, you do not need to bring the patient into the office to screen them for sleep apnea. So they even had us write this in the title of our paper, the importance of medical history over symptoms. Okay, and our nearest competitor for this is the Stop Bang tool, which is 8 features that does include patient-reported symptoms. So in order to evaluate Stop Bang, you need the patient to come into the doctor's office. And the Stop Bang tool has a false positive rate of 46%, which is much higher than the 20% that the doctors wanted. Okay, so the Journal of Clinical Sleep Medicine published an editorial recently about our work. This was written by 3 sleep medicine doctors that are experts in the field that we have never met. And they kind of hit the nail on the head where they said, our tool could be integrated into the electronic medical record, flagging high-risk patients. Okay, so you can automatically screen huge numbers of people because of the work that we've done. Okay, let's switch gears. Last application, which is ICU seizure prediction. Now here we're switching over to risk scoring. And our goal here is to predict whether a patient in the ICU is going to have a seizure within 24 hours. The patients are monitored with EEG. They have electrodes that are measuring electrical signals in their brain. They're looking for patterns like LPDs, which affect one side of the brain, or GPDs, which affect both sides of the brain. And we were working with neurologists at MGH, but they gave us a data set that was from a consortium from several different hospitals that had over 5,000 patients in it that were monitored for at least 6 hours each. And we know whether each patient had a seizure. Okay, so with any risk prediction model, you would expect that as the score goes up, the risk should go up too, right? It would be pretty weird if a score of 7 was less risky than a score of 6. It doesn't make any sense. But that doesn't always happen. And in particular, when you try to round logistic regression coefficients, it really messes up calibration. Okay, so calibration is when the predictions and the predicted probabilities and the true probabilities, it's how well they match. So here's an example where we used a variant of logistic regression to get a model here. And I'm showing you predicted risk versus the true risk, and it's supposed to be a straight line. But it kind of goes up and down, so that's not so good. This means that a higher predicted risk from the model leads to a lower true risk in the data. So that's not exactly what you want. But it sort of goes up. I mean, these gray lines are from different subsets of the data, so you can kind of see it goes up. But then when you round it, well, first of all the small coefficients go to 0, so then it just wipes out the whole model and you get something that's garbage. So that's not a good idea. So what you might do instead is take all the coefficients and multiply them by a constant and then round. But even if you do that, the calibration gets really messed up. Like here, it's all over the place, and then there are these gray curves that are like this, and that's not what you want. But luckily, because we're actually optimizing for calibration, our model doesn't have that problem. And this model is called 2 helps 2b. So 2 helps is the 2 hertz there, 2h, E, L, P, S, and then the 2b is for the 2 points for the b. Okay, so you can memorize the model by the name. And as you can see, as the predicted risk goes up, the observed risk also goes up. It's very nice. And then these are ROC curves, and even across folds, very, very consistent. Okay, there is no predecessor for this application. Like, there's no ICU seizure risk model out there, so this is the first one. Okay, so what I'm showing you is a snapshot from an editorial that was published in JAMA Neurology about our work. And these authors emphasized cases in which, for instance, a logistic regression model was used in the past, but the formula was very difficult to calculate on an individual patient, which limited clinical utility. And then they also they actually spent a long time in their editorial talking about the clinical utility of our work. And they mentioned in particular that it could help figure out how much we should monitor patients with EEG, and also guidance as to what patterns to treat more effectively than others, like patients with a high score could get medication. And it also says, this score can be easily added to an EEG reading to help to explain to the clinician what's going on. Okay, so before I finish, I wanted to address a challenge that was brought to us by the judging team, which is to try to quantify the impact of what we are doing in dollars. Now, dollars is not the right unit of measurement for these kind of predictive models that are meant as decision aids, but I thought, this is a challenge. Let's try to do it. Okay, so in order to do this, we have to come up with the cost of a false positive and a false negative, and the benefit of a true positive and a true negative. Okay, and these numbers are really hard to calculate. So in order to do it, you have to establish a very clear causal relationship, and then actually go and find some very trustworthy statistics. But luckily for us, there was one, out of all the models I showed, there was one clear causal relationship, which was that sleep apnea causes car accidents. And in fact, there have been about 30 studies on the effect of sleep apnea on car accidents, and most of them estimate between a 2 to 5 times higher risk for untreated sleep apnea patients than for either treated patients or the general public that doesn't have apnea. Okay, so I said, fine. Let's say that so now we know, because of our work, we know that you can launch an automated screening tool for apnea within the medical record. So people who've never been to a sleep lab, we could screen them for sleep apnea. So let's say that we launched this tool across the entire United States. How much would we save through reduction in car accidents in a year? All right, so I combined a whole bunch of publicly available data in order to do this. And what I calculated was the cost of a false positive screen. So this is people who we brought into the clinic who didn't have sleep apnea, and we had to charge $1,000 each for the polysomnography tests of those people. And then the value of the accidents reduced was either 9.56 billion times the true positive rate of the test for just economic costs, or 33.1 billion times the true positive rate for including quality of life valuations. So this is like the value of people's lives. And for the screening test that we actually constructed, the cost was somewhere around 1.5 billion, and the benefit was either 5.87 billion with just economic costs, or over 20 billion, including the value of lives saved. And that's only within the first year. Right? Every year after that, the people who were diagnosed with OSA continue to have accidents at the lower rate and not the higher rate. And so you continue to reap the benefits every year and don't suffer the costs. Okay, so just to summarize, I presented 2 machine learning models for producing scoring systems, SLIM and RISC-SLIM. No rounding, no constraint violations, no heuristics, no suboptimal solutions, and it makes it really easy to work with domain experts because you ask them, why didn't you like this model? And then they tell you, and you put in a constraint and you make sure it never happens again. For recidivism, we showed that there's no need for proprietary or black box recidivism risk models like COMPASS, and that it's possible to have transparency in the justice system with no sacrifice. And people are really starting to listen to this message. In ICU seizure prediction, we provided the first EEG monitoring tool to predict seizures. And then for sleep apnea, we were able to show that automated and transparent sleep apnea screening is possible. These models are faithful to a century-old scoring system form that's been used in many, many different domains, including healthcare, criminology, credit scoring, and many others. And finally, software for all of our methods is publicly available.